Continuing with our discussion then of Markov chains, what we're going to look at today are what are called absorbing Markov chains. And a quick definition of what we mean by an absorbing Markov chain. Is once a certain state is reached, it is impossible to leave that state. And a great example of what we mean by once a certain state is reached and you'll never leave that state is what we call the gambler's ruin. Here's the story. A gambler has any amount of money. We're going to say $200. And he risks $100 at a time. Until he is broke or has, well, let's say $400. So this gambler is going to play until he doubles his money or until he's completely broke. The catch is the probability of winning is only 0.45 or 45%. So what I want to do first then to kind of model this is we're going to make a transition matrix that shows how this gambler goes from one game to the next. So the gambler could have $0, 100, 200, 300, or $400 before the game. And then after the game, he's going to have either 0, 100, 200, 300, or $400. So we're going to see what we go from before to after. Now, going across the row of the 0, once the gambler is broke, he's going to continue to be broke afterwards. There's a 100% guarantee that he's broke. He's not going to go up to 100, not going to go up to 200, not going to go up to 300, and not going to go up to 400. The gambler is broke. However, if he's got $100 before the game, there's a 55% or 0.55 that he'll lose and drop down to $0. Zero probability that he stays where he is, but there's a 45% probability, 0.45, that he'll go up to 200 with a win. And he can only go up or down $100 because that's all he's risking at the time. Now, if he has $200, he's not going to drop to 0, but there's a 0.55 that he'll drop down to 1 after the game is over. A 0% chance he'll stay the same, and a 0.45 probability he'll go up to 3. And you start to see the pattern. We can fill in the third row with 0, 0, then there's a 0.55, he'll drop down to 2, a 0, he'll stay at 3, and a 0.45 that he'll go up to 4. But once he reaches 4, he has doubled his money, so he's going to stay at 4, 100% probability, 1.0 all the time. No loss to 0, 1, 2, or 3. So this is the transition matrix of before the game to after the game. And so we can see if he has $300 at any given point in time, there's a 55% probability he'll drop to 2. and then he'll play again with 2. There's a 55% probability he'll drop to 1, but maybe then he wins, so from 1 he wins, takes that 45% probability to 3, and so on and so forth. And so from game to game, he's going to bounce all over this matrix until eventually he reaches what's called the gambler's ruin. Either he doubles his money to 400, or he loses all of his money to 0, and once he reaches that point, he stops. So, if that models game to game, what we might be interested in is what is the long-term trend. The solution matrix, or the long-term trend of what's going to happen to this matrix as he plays over and over and over and over again. And you might remember that's when we took the transition matrix to some large power. We can't really type infinity in our calculator, but eventually this is going to level out at some equilibrium point. So let's program this on our calculator and see if we can agree on an equilibrium point. We'll go matrix, go over to edit. This matrix has 5 rows and 5 columns, and the entries are 1, 0, 0, 0, 0, 0.55, 0, 0.45, 0, 0, there we go. Then it's the 2 is a 0, 0.55, 0, 0.45, 0. The $300 row is a 0, 0, 0.55, 0, 0.45. And then the last row is 0, 0, 0, 0, 1. Going second quit to get back to the home screen, and I like to look at that matrix to make sure I typed it in right, so I'll select that first matrix and hit enter just to make sure it looks right. And you see the 1, the 5, 5 going diagonally, the 4, 5 going diagonally, and finally the 1 in the bottom right corner. So that matrix is typed right. We're going to raise it to some very large exponent. Let's go to the 100th power just to see what that does. Think for a minute. And we got these e-16s. That means times 10 to the negative 16th. We're getting really close there to a 0. Let's go to a bigger power. If I thought this was the final answer, I could hit math fraction. But it's still going to give me, it gives me some fractions, but it also gives me some decimals. So we're not done yet. So we're going to raise this to another power. Just picking another large number. Let's go 40th. That's actually going to take us to the 40 times 100, 4,000th power. And now if we hit math, fraction, we do get fractions for all of our entries. And what's interesting is the center column all went to 0. On the outside, we've got 3311 over 4040, 121 over 202, 1331 over 4040, and if we scroll down, 0. On the right side, we've got a 0, 729 out of 4040, 81 out of 202, 2709 out of 4040, and then finally the last entry is a 1. So if I write this down, copying from my calculator, we've got a 1, 3311 out of 4040, 121 out of 202, 1331 out of 4040, and finally a 0. Then we had 3 columns of zeros. And then finally in the end, we've got a 0, then there was a 729 at a 40-40, then there was an 81 at a 202, then 2709 at a 40-40, and finally a 1. Now putting on the before after labels of 0, 100, 200, 300, $400, 0, 100, 200, 300, $400. What this is going to tell us is in the long run, if at any point he has $200, there's a probability of 121 out of 202 that he's going to come up with financial ruin. There's also a probability of 81 out of 202 that he's going to be able to double his money and walk away a winner. In the long run, we can see what is the probability we go from any value to financial ruin at 0, or from any value to doubling the initial $200 to $400. So that's what this is going to illustrate for us, is the probabilities that we get to ruin or absolute gain. However, this is kind of redundant in that we've got this annoying center of all these zeros. So sometimes we simplify this down to a simplified solution matrix, where we just show the absorbing states on the top The absorbing states are the ending states. We're either going to end at 0 or we're going to end at 4. And the non-absorbing states on the side. And this is going to make it a little bit easier to play with. So the non-absorbing states are $100, $200, and $300. And from there, they're going to go to 0, absolute ruin, or 400, absolute gain. So the probability that we go from 1 to 0 was 3311 at a 40-40. And 1 to 4 was 729 at a 40-40. The probability we go from 2 to 0, absolute ruin, is 121 at a 202. And from 2 to 4 was 81 out of 202. From 3 to ruin is 1331 out of 40-40. And from 3 to absolute gain, we just have to win one game, is 2709 out of 40-40. And then this solution matrix gives us the same information, a lot more condensed, without all of those extra zeros and the 1 on the diagonals. So then we can see really clearly here, just to emphasize, if the gambler has $300, the probability of ruin, actually I can even write it in our probability notation, the probability of ruin, or 0, is equal to, from 3 to 0, the probability of ruin is equal to 1331 out of 40-40. We can also see that the probability of success is equal to, and that's from 3 to 4, 2709 out of 40-40. And so we can interpret this solution matrix in this way. Now, depending on the context, though, it might be rather difficult to raise this matrix to a higher power and a higher power and a higher power, and we kind of waved our fingers and said, yes, that's the steady state, the equilibrium state of the long-term solution matrix. However, there's a more mathematical way to actually find the solution matrix. And so we are going to find the simple form, that's the orange one that we just found, of the solution matrix. Now the method here is easy to use and employ, especially with a calculator. However, the process, showing why the process works, is beyond the scope of this course. We'd have to take a linear algebra course to really get at what's happening here. Since we don't have that, we're just going to look at the process and go, hey, that's kind of neat that it works. Here's what we do. We're going to follow 3 steps. First step, we are going to reorder the matrix, the original transition matrix, to look something like this. We're going to make it an augmented matrix with 4 sections. How we're going to set those 4 sections up is the top and the left corners are going to be the absorbing states. The bottom and the right are going to be the non-absorbing states. So when we do that reordering, what's going to be neat that happens is the top left is going to turn into the identity matrix. The top right is going to turn into what we're going to call the zero matrix. It's going to be all zeros up there. The bottom 2 matrices are going to be what are of most interest to us. We're going to call the bottom left matrix A and the bottom right matrix B. Those matrices A and B are going to help us find the solution matrix. First, we're going to do what is called finding the fundamental matrix. And what the fundamental matrix does is it tells us the average number of games to absorption. Is that a P? Absorption? Yeah, absorption. In other words, if I have $300, how long is it going to take on average for me either to lose it all or to gain it all? How many games? And the way we find the fundamental matrix is we're going to use this formula, and our calculator is going to be really nice for this. The fundamental matrix is equal to, in parentheses, the identity minus matrix B, and then the inverse. This is going to be something you'll want to have memorized for a test. The fundamental matrix is I minus B inverse. With the parentheses, that's important. We got to do I minus B first, and then we take the inverse. Once we have that I minus B, then the simple solution matrix is going to be equal to the fundamental matrix on the left times the A matrix on the right. Remember, A and B come from the bottom row of the augmented matrix when we reorder everything, when we put the absorbing states in the top left and the non-absorbing states in the bottom and right. So FA, that's probably something else you'll want to have memorized for the test. Solution matrix is F times A. When we do this, the calculator is going to do all the hard work for us, and we will end up with the simple solution matrix. So let's give this a try with our gambler coming to ruin. Just for the sake of remembering that transition matrix from up above that we found, we could go from 0, 1, 2, 3, or $400, and then end up with 0, 1, 2, 3, or $400. We had a 1 staying at 0. then a 0.55, 0, 0.45, 0, 0. The next row kind of going diagonally, 0.55, 0, 0.45, 0. The next row 0, 0, 0.55, 0, 0.45. And the fourth state is a absorption state, 0, 0, 0, 0, 1. So we are going to reorder this into our new matrix, which has absorbing states in the top and the left. Actually, let me see if I can get a little more space. We are going to put the absorbing states in the top and the left, and the non-absorbing states in the bottom and right. So we want the absorbing states in the top and the left, and the non-absorbing states in the bottom and the right. Who are the absorbing states? Well, the absorbing states are where we get stuck. So 0 is an absorbing state. 4 is an absorbing state. Those are our absorbing states, 0 and 4. Then 1, 2, and 3 are the non-absorbing states. So 0 and 4, and then 1, 2, and 3 are the non-absorbing states. And so when we split our matrix into our augmented matrix, you see the top left is the absorbing states, and the bottom and the right are the non-absorbing states. Now we just have to fill in our numbers. We can use our table to go from 0 to 0, that was 1. To go from 0 to 4, that was 0. To go from 0 to 1 was 0. 0 to 2 was 0. 0 to 3 was 0. The fourth row then, no, be careful, the order's been changed here. From 4 to 0 was a 0, and from 4 to 4 was a 1, and 0, 0, 0. Notice, just like the formula states, we've got the identity in the top left corner and zeros in the top right corner. And our A and B matrices are going to be what comes out in the bottom here. So going from 1 to 0, there was a 0.55 probability. From 1 to 4, no chance of that. From 1 to 1, no chance of that. From 1 to 2, there was a 0.45 probability. From 1 to 3, there was a 0. It doesn't really look like a 4. There we go. From 2 to 0, no chance. From 2 to 4, no chance. From 2 to 1, that's a loss with a probability of 0.55. 2 to 2 is not happening, but 2 to 3, that's a win, probability of 0.45. To go from 3 to 0, not a chance. From 3 to 4, 0.45. From 3 to 1, not a chance. From 3 to 2, that's a loss at 0.55. And then from 3 to 3, the probability is 0. So what I want to notice here is this matrix gives the same information as the matrix above it. We've just reordered the numbers. Put in the absorbing states where you get stuck in the top left, and the non-absorbing states in the bottom and the right. When we do this, we can clearly see that A is the bottom left matrix of 0.55, 0, 0, 0, 0.45. B is the matrix right next to it, which in our case is 0.45, 0, 0.55, 0, 0.45, 0, 0.55, and 0. In order to do this on our calculator, we're going to need an identity matrix that matches the B matrix in size. It's the same size or same dimension as the B matrix. So the identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. The other matrix we need is F. Remember, F is I minus B inverse. We're going to have the calculator do this part for us. As we program our calculator, you remember on that list of matrices, there are lots of matrices we can choose from. A, B, C, D, E, F, and it goes all the way down. I strongly encourage you to use the letter that matches the letter we're using here. So in matrix A, we're going to put matrix A. In matrix B, we're going to put B. In matrix I, we're going to put the identity. So first let's program matrix A. So second matrix, go over to edit. Matrix A has 3 rows and 2 columns in it. 0.55, 0, 0, 0, 0, 0.45. Enter. So that's matrix A. Now we'll move the calculator over so we can see B. We'll program matrix B. Second matrix, edit. Scroll down to matrix B. B has 3 rows and 3 columns. It is 0.45, oops, missed the decimal point, 0.45, 0.55, 0.45, 0.55, 0. Second quit. We also need to program the identity matrix in. So we'll go second matrix, over to edit. And the identity matrix, I like to put it into I. That way I know it's the identity matrix. If you scroll up, you can get to I really quick. To program matrix I, which is a 3 by 3, oops, not 33, 3, enter, by 3, 1, 0, 0, 0, 1, 0, whoops, missed a 0, 1 in the center, enter, 0, 0, 0, 1. And so there's the identity matrix. Second quit. So now we've programmed A, B, and the identity. To get F, we're going to type it in just like the formula says. We open up a parentheses, we grab the identity matrix, second matrix, scroll up to get to the identity quickly, minus matrix B, second matrix, matrix B, enter, close the parentheses, and we are going to find the inverse. So we use the inverse button, the x to the negative 1. And when we hit enter, we get the fundamental matrix. I'm going to round to 2 decimal points and go down the columns here. We got 1.49, 1.09, 1.49, 1.09, and the last one's 0.60, 0.60, 89, 1.9. So it's 0.89, 1.98, and 1.09. And then the third column, calculator's playing tricks on me here. There we go. Third column, 0.4, 0.89, 0.40, 0.89, and finally 1.49. And now we have our fundamental matrix. Just a quick recap of what the fundamental matrix means. Remember that 1, 2, and 3, the non-absorbing states, were our headers for B. Same thing for here. So looking at what this fundamental matrix means then is, for example, if you look at the third row, first column, we see 0.6. That is the average number of times the gambler will go from 3 to 1. before they're absorbed. Before absorption, going from 3 to 1, 0.6 times. Similarly, if we look at the second row, second column, for example, the 1.98, the number of times the gambler will go from $200 to $200 back where they started, on average, will be 1.98 times before they finally double their money or come to complete financial ruin. It's the number of times you make that movement from a certain state to a certain state. How many times you will do that before you're completely absorbed into the game. But that's not what we were looking for. Our final solution that we were looking for was FA, the simple solution matrix. So let's find FA, the simple solution matrix, which we can do on our calculator. You should still have the F up on your screen. We can then multiply that, so we'll hit second answer, the previous matrix, times second matrix. I guess you don't have to hit the times. Multiplying by matrix A. Enter. Gives you this ugly guy, but if we hit math fraction, we get the same simple solution matrix we had before. So we can copy this down. We had 3311 out of 4040, 121 out of 202, and 1331 out of 4040. That's the first column. The second column, 729 out of 4040, 81 out of 202, and 2709 out of 4040. The absorbing states then are the columns. The non-absorbing states are the rows. So the rows are 1, 2, 3, and the absorbing states 0 and 4 are the columns. So we can see the probability of going from 3 to financial ruin is 1,331 out of 4040. The probability of going 2 to doubling your money is 81 out of 202. This is how we can work with absorbing Markov chains. We follow this three-step process where we reorder everything so that the absorbing matrices are in the top and the left, and the non-absorbing matrices are in the bottom and right. I'm sorry, the non-absorbing states. When we do that and split it into an augmented matrix, which separates into those 4 parts, they're all different sizes. The fundamental matrix then is I minus B inverse. And finally, the solution matrix is FA. And the order is important in all of these formulas. So make sure you're watching out for that. So on the homework assignment today, you get a chance to play with some of these absorbing Markov chains. Take a look at practicing them. Learn how to use these formulas. The process is really simple. We're programming it into our calculator. Just need to practice so you know how to program it in your calculator. You need to know the formulas, and you need to know how to interpret the result. We'll see you tomorrow in class for questions.